Jatin G. Bhatt with us, who is the speaker for the session too. So welcome to the session. So a brief about sir is Dr. Jatin Bhatt is specialized in metallurgical and material sciences. He's currently working as Associate Professor, Department of Metallurgical and Material Sciences, VNIT Nagpur. He's also Associate Dean, Industry Institute Interaction and Alumni at VNIT. An alumni of IIT Madras and Banaras Hindu University, he is having an experience as research scientist at SSN Research Center and Research and Development Engineer at Kalyani Carpenter Special Steels Limited. His areas of interest are bulk metal glass, metal matrix composites, nanomaterials, semiconductor materials, metallurgical, thermodynamics, kinetics, non-equilibrium materials, processing and technology, metallic glasses. So added to his credit or are 716 citations in Google Scholar with 17 H index and 25 I-10 index papers. So we are very happy to have you on the session.
Thank you, Sweta.
Welcome, sir. A warm welcome.
Thank you, Sweta. And thank you, Dr. Gupta, for inviting me for this online talk on recent developments of nanocomposites and smart materials in aerospace industry. I hope I'm audible to everyone here. Right, Sweta? I'm audible?
Yes, sir. You are audible,
Right,
sir.
right. So basically, I was talking to Sweta. She told that most of the people who are participating are from academic background as well as they have background of mechanical and aerospace engineering. And I am odd man out here because I belongs to metallurgy and materials engineering. So my language and of interaction probably may be a little different, but I would like to see that how I can make it simple, because making things simple will make us to understand what exactly are the challenges in aerospace materials. And because Dr. Gupta has named this particular faculty development program as nanocomposites and smart materials, these are very huge responsibility on composite material, because in aerospace material, a majority of materials are used in the form of a composite. So, but nanocomposite has its own strength and challenges. And of course, the smart materials, when it comes to real use in real-time structures, the what type of challenges are faced, because all materials that we are going to use in aerospace material are having certain properties, and we do require to understand those properties. So let us see, before you take any material for high-end application, what are the basic things that we must keep in mind before we apply those materials for application. So that is very important. So this is what my plan of presentation. General challenges in material. Nanostructured, what exactly is nanostructured? I will give some few minutes in this because it is important. Every time we have to, whenever we want to discuss about nanomaterials, we do have to talk about what is happening in nanomaterials and general characteristics of nanomaterials, few slides, then something on the real-time materials in the form of 2-dimension and 3-dimension structures I'll be talking about. I'll give some few examples on synthesis and general characteristics. Then, a very important thing is, because the material that Dr. Gupta has proposed is nanomaterials, and the most of the important challenge that comes in nanomaterials is its instability. Okay, the stability is a question. So you have to make up material such that it can be stable at the working environment, and how harsh the working environment is in aerospace material. So we'll be touching a few points on melting point, and of course then we'll be talking about your favorite link to any material mechanical properties, and then I will conclude my talk. So everybody is aware about such type of slides. I have just borrowed from one of the running, website, Boeing 787 Dreamliner. What is the proportion of materials that are used is highlighted here. So, we are more interested in this particular graph. So you can see that almost 50% of the material is composite here. And this is a real, and this is timely faculty development program, because we require to probe exactly what type of composites in nanomaterials are available, and what are the present challenges present in it. Otherwise, you see, you have another metallic materials like steel, then titanium, then aluminum. Composite and aluminum you use because you want to take advantage of high strength to weight ratio. And now you are not using pure aluminum as such, you are using aluminum alloy, aluminum copper alloy. And then there is some parts where you require to use for load bearing application, you use steel. Otherwise, titanium is also light metal, so you use titanium based alloy along with vanadium or aluminum or nickel or chromiums. So it all depends on what type of application it is going in. You have to design your alloys as that. But we will be talking about composites. So this is a very interesting part, that 50% of the body is composite. Now, this composite today that people use are glass fiber, carbon, carbon, epoxy, resin type of composites, or they can also have some type of graphite in carbon, graphite in, carbon matrix composite, graphite in aluminum matrix composite. So there are different definitions which can qualify to call as a composite, where you require to have lightness, that is, it should be light, its density should be less. Apart from that, it should also have sufficient desired strength to withstand the properties that is required in aerospace application. Now, here is important thing. We know materials, we keep on probing new materials. We always want to see what are the problems with present day materials, and we want to replace them with newer materials. Newer materials must pass through, test, the test that is designed so that you can find out whether it can be operated at the temperature or the environment or the stress level in which you want to use that particular component. So today there are issues. These issues are we don't get enough strength, though we are making it lightweight, but you keep on changing. You have to keep on changing the material, and sometimes untimely problem comes during operation. Fatigue, which is an important property that is required in material, most of the time such type of properties are not met by the components that you are using in aerospace material. There is always trade-off. You are able to create good strength, but the density of the materials is large. Then it does not qualify it for aerospace material. If you make density less, then you lose the mechanical properties. So there is always trade-off. So there is a very thin window where you can keep a balance between both the lightweight as well as strength that is required in your materials to be used for aerospace application. So the challenge is when you are talking about composite, and to be precise, when we are talking about nano composite, I'll be talking about nano composite here. I'll be talking about nano-based material here. And I will be telling you that before we take any material in hand, its internal characteristics are very important to understand whether you can use that particular material for high-end application or aerospace application. So the main roadblock for widespread adoption of nanomaterials is the uncertainty over their environmental and health implications. Still, this study, as far as such niche application is concerned, aerospace application is concerned, there is a lot of uncertainties there. And I will tell you why this uncertainty is there, because there is no repeatability in property that we observe. Nanostructured material, because they are very smaller in dimension, and the goal for manufacturing the nanostructured material, you have to produce them in such dimension that there should be a consistency in dimension. There should be consistency in, why I'm saying dimension, because structure derives from dimension. If your dimension is not under your control, your structural, what structure I'm talking about is the material structure. So your material structure is bound to change. You you make same material from three different processes, you will see the same material will be having different property. You make same material at different time, until unless you have very good control over process, you will see that your material property is keep on changing. That is the meaning of unrepeatability. So there is a problem that the repetition in properties are not consistent. It keeps on changing from one lot to another lot, and electronics industry have taken good control over repetition in property, and due to this we are able to see some high-end electronic gadgets in market because they are able to control property at a smaller scale. You talk about certain companies like Intel or Global Foundries, they have controlled the environment. That is why they talk about clean room facilities, where they are able to make their product with the dimension, with the dimensional accuracy, with the purity level, and with the type of constraints with impurity they are going to face. They are able to control it. But when we talk about bulk materials, aerospace materials, we consider we are going to use bulk material in aerospace materials. The cost of manufacturing, if you start talking about clean room facility, the cost of component will rise. So that is why we have to look for opportunities where we can make this material in open environment. When you talk about open environment, you are always, and you will always end up in some type of interaction with environment. Okay, so that is the reason I am talking here about uncertainty. See, this particular report challenges I have taken from AzoNano. One article was there, a very interesting article. So you can understand that there is always uncertainty. Again, there is no, because you are going, when you want to make any component, you want life in that component, which means you require that particular component is to be time tested. You require time. You have to give time, which means a particular time frame must be established where your component will retain its stability. So this is yet to get established. And the type of environment where aerospace materials goes are not so simple. They are under huge change in environment as compared to ambient environment we are in. Your pressure is different, temperature is different, your load interaction is different. So, we require to establish in nanostructured material that whether it will retain stability at that particular time scale and at that particular environment is yet to be established. And also, as I mentioned we are already this aerospace materials are under harsh condition in space. So we have to study properties, dynamic properties. Yes. So that we can design our material as per the application. So this is always a problem. Okay. So these are certain challenges are there, but this does not mean that we should stop looking into this material, because what advantage this material gives us is with a smaller dimension, you can achieve good strength. Okay, because you are able to take advantage of properties at very smaller dimension. So if you can do that, you will be able to make materials that can be used for application where such type of challenges are there. So let us quickly see what I am talking about, because this is a very interesting thing. Your material which you are going to use, of course, it is going to interact with environment, and surface of the material will always be in touch with environment. When I talk about surface of the material will be in touch with environment, which means your material is made up of the species, what we call as elements. Elements combines to form alloys, and then alloys, they have certain structure. So these structures are going to get influenced by the environment. Now, we are talking about structures which are in nanoscale. What is going to happen when you are going to make the aerostructures in a form of a nanocomposite? When you say nanocomposite, which means your components which are made of material will be having nanostructured features present in it. And when they have nanostructured features present in it, so this is a very important criteria that comes into picture. As you keep on going from little bigger dimension to smaller dimensions like this, because when we talk about nanocomposite, we talk about similar dimension. Okay, that you are going to make some precipitates in the material, you are going to create some type of new material. This new material will be having features. The smallest feature will be of similar dimension. Now there is going to be the enhancement in your surface area to volume as you keep on going from this to this. Now this poses a problem. This poses a challenge. Why? Because surface area to volume ratio has direct link with surface energy. So your surface energy is a function of surface area. So you see that your surface area is increasing, which means your surface energy of that particular region of interest will increase. When the surface energy increases, it is looking for some type of interaction with environment because it wants to stabilize itself. As far as material stability is concerned, it is not like that you take a material is not always stable. It always looks to in the environment for stability. So if you have such huge surface area and your surface energy is high, of course it is going to react with the environment. And when it reacts with the environment, if environment helps us to stabilize the material, not to react further with the environment, then it is good. But if environment is creating some type of reaction and that reaction product is hazardous for the component, then it is a problem. So we require to understand that how to make materials so that it can automatically become smart. That is how Dr. Gupta has kept this name timely, nanocomposite and smart. So you have to make your material such that in smaller dimensions so that it can, if it is getting challenged by the environment, automatically it should able to heal itself with the help of surface area or surface energy it has. So this is something, in similar line, we are going to talk about in our presentation. Now, interestingly, you see that I have taken a simple example here. Because we understand seeing is believing, experimental results, what they tell can be extrapolated in order to understand the real-time problem. You see now you have taken the bigger dimension gold, like you go to the bigger dimension like 100 nanometer and above, you will see that it has a melting point of something like 1320 Kelvin. As you keep on decreasing the dimension of the particle, what you see is there is a decrease in melting point of gold. Now you see the challenge. I was telling you some time back, you are planning to make a nano composite. You want strength. Strength is a function of microstructure. How your microstructure is. Strength is also the function of bonding. How the bonding is present in your material. Now, if you change your material from bigger dimension to smaller dimension, what is going to happen? Your bonding characteristics are also changing. Now, this is another challenge that you want to make nano structured material. When your bonding characteristics is changing, automatically your strength is going to change. Your material will be having higher strength over here and it will get converted into lower strength. Now, you see, these type of examples are important where our motivation is to decrease the melting point of material so that better energy management can be done in order to make those material. But when you want to apply nanostructured material in the application where loading is concerned, then lowering the melting point is a challenge. So when you talk about nanocomposite, you are going to use nano feature. And when you're going to use nano feature, they are going to have lower melting point. If they are having lower melting point, they are definitely going to have lower strength. This is just information, one information I want to share with you. This is not observed only in gold, it is also observed in lead, it is also observed in copper, it is also observed in bismuth and silicon. Now, this is a good news for the people who are working in tungsten type of system. The tungsten has a melting point of 3400 degrees Celsius. Everybody were using incandescent lamp in their house. Now we are replacing our incandescent lamp by LED bulbs. But still many places tungsten filaments are used, bulbs are used. We require to manufacture them. And manufacturing of such material relies on the temperature of process. Now, if such type of benefits we are getting by reducing the dimension, we can decrease the melting point. So this is a good news for tungsten based material. Tungsten, tantalum, all high melting point metal or material can take advantage of this reduction in melting point. So this is one good thing, as well as when you talk about strength related application, this is not a good information that your material is going to lose its strength with decrease in dimension. Now you see, when we talk about composite, we talk about embedding either particulate, either some type of single crystal or some type of wire or some type of rod as a standalone feature in the matrix material. And then we talk about nanocomposite. So here is something, you embed particles in matrix, nanoparticles in matrix. Say you have a matrix of aluminum and you have embedded some type of oxide, say for example aluminum oxide. Just I'm giving you idea because this is the way composites are made. You end up in getting nanocomposite, while the nanoparticles melt below the melting point temperature. Now that is what the problem I was talking about some time back, that you have a nanoparticle that, and you have a matrix material. Now matrix material is a bulk material. It's a continuum material. Your nanomaterial is a discrete material. You are bringing your discrete material in contact with continuum material. You are creating an interface between the continuum material and the discrete material. Your continuum material will remain stable because it does not have large surface energy, but your discrete material has large surface energy. So there is going to be something happening at the interface between the nanoparticle and the matrix material where the melting is going to start. Now again I am saying why this is important concern to us, because when we talk about nanocomposite, we talk about strength in terms of entire composite. Now in composite material, both particulate or whatever secondary phases are there and is in equilibrium with your matrix material. When I say this, which means there is a good bonding contact between the particulate and the matrix material. If one of the particulate species starts melting at all the places, what is going to happen? You are going to loosen your composite material. You are going to make your composite material to fail. So this is a very important criteria that we must remember, that when we talk about, that is why there is a relationship. I will not go into the depth of relationship, but this is very interesting relationship. It talks about that if this is the melting point of the modified material, and this, or you can also call this an extended material. Extended material means a bigger material broken down into smaller material becomes an extended material, and D naught is the original melting point of material. This clearly indicates that as you keep on reducing the dimension of the material, what is going to happen? This particular parameter is going to increase. 1 minus this parameter will decrease. Automatically, the melting point of the extended material is going to decrease. So whatever we have observed here is basically coming from this relationship. Now, important message which I want to tell you from this equation is surface. I mentioned you sometime back surface area to volume ratio. Then smaller is the R, your surface area is increasing, your surface energy is also increasing. This is very important criteria. You have to understand. That is why your surface characteristics you have to understand, because there are different type of surface contact. It is not mandatory that when you embed your material will melt first. It all depends on how good contact the material or embedded material is making with the matrix. If it is not making very good contact, automatically there is going to have some type of dislodgement of the particulate. Now, this is all decided by the contact angle. Now see, so many things are there. You want to make composite, you want to make nano composite, you want to make nano feature, you want to make two body system. One is matrix, another is particulate. This particulate, how it is embedding is decided by the contact angle. So this is what I mean to say. When we talk about matrix material and when we want to embed any particle into it, the contact angle is a very important criteria. And this contact angle decides whether your embedded particle is going to melt or embedded particle is not going to melt. So there is a interesting relationship here. This is a well-known relationship about the contact angle and the surface energy of liquid matrix interface, solid matrix interface, solid liquid interface. So this cos theta is basically derived from liquid matrix, solid matrix, and solid liquid interface. Now, if your surface energy of solid matrix is greater than of liquid matrix, this is going to happen. The melting temperature of embedded nanoparticles should be lower than the bulk melting. So we don't want this to happen. If this is happening, the melting temperature of the embedded net should be higher than that of bulk material. So this is good news for us. So when you want to make any composite material, you should also keep in mind that the type of contact the particle is going to make or any type of wire or rod is going to make with your matrix, how is this contact angle? How stable is this contact angle? If this contact angle is not stable, your composite is bound to fail. So when we talk about nanomaterial, nanocomposite to be used for any application, especially in aerospace application, where I mentioned some time back that many challenges are there because of harsh environment, you always come across this type of problem, and we require to understand the contact angle. And information about the contact angle can be understood with the help of crystal geometry. I will not go into that, but I would like to just tell you that if you want a good understanding of contact angle, you require a knowledge of surface energy. If you want to have a good knowledge of surface energy, how good is the surface energy, practically you can determine, but at the same time, if you know individually about the how is atoms are placed inside the material, what is the distance between the atoms that are placed inside the matrix material, and what is the distance of the atoms that are placed inside the embedded particle. If they both are matching with one another, there is always going to be good bonding between the matrix and the particle. If they have a huge mismatch in their dimension, there is going to be stress at the interface and your material is going to get dislodged from that particular site. So this is a very interesting thing that during the design of material, this has to be kept in mind when you want to use it for strategic application like aerospace material. So melting temperature can be either increased or reduced with respect to bulk material depending upon the surface energy of solid liquid interface and how it is related to matrix. So this gives you some idea about that something is going to happen inside the material at the smallest level. That is why now I am going to the atomic level, because nanostructured material, when we talk, we talk in terms of nanostructure, that is nano dimension. But now the other smallest dimension where your nanomaterial is made up of is of atoms, the cluster of atoms they have come together. Now you imagine a situation you require to control them to get the desired type of cluster, desired shape of cluster, desired structure of cluster, desired chemistry of cluster. At the end, when you have control over this, you will end up in getting the desired chemical properties, desired physical properties. This is very important. So if you don't know how to design the material from the material science background, then it becomes easy to apply those materials to the application where you require high-end properties. Now, coming to this, because there are different type of nanostructured materials, but the materials which are of interest to the aerospace application is two-dimensional structures and three-dimensional structures. Two-dimensional structures, basically films, thin films. This particular materials goes in device. Okay, if you are using any electronic device in aerospace industry, definitely they will be made up of thin films. So this is one of the examples of nanomaterials, where you have silicon nitride, you have the matrix of copper, and then you have tantalum. Such type of very different type of examples are there. Just to give you idea that the nanostructured material is not only the bulk material, they are also in form of 0D, 1D, 2D, and 3D. We are not talking about 0D and 1D, but we are talking about 2D and 3D structures, because they are basically used for surface modification. So if you want to do any surface modification, you will rely on 2D structures. And if you want to do any bulk modification, you will rely on 3D structures. So this is an example of three-dimensional structures where all the dimensions are greater than nanometer. This is understood. So it can also run in meters. It can run in centimeters. Only the features that are present inside it, they are of nanostructure dimension. So this another example, you see here 500 nanometer, 0.5 micron meter. And this is, I'm sharing with you an example here, because when I say that you require to manipulate or manage this structure, it cannot be done macroscopically. It cannot be done with the help of naked eye. You have to understand what is happening inside the structure. So if you want to know what is happening inside the structure, you have to rely on what is called transmission electron microscopy, where electron is going to find out the type of grains that are present inside the material, how they are present inside the material, how they are interfacing with another particle. All this information can be generated, and this is very important if somebody wants to design any material. One has to understand the structure. Without a structure, you cannot derive property. You know that structure property relationship. Okay, so structure has to be managed, the structure has to be understood, and has to be manipulated accordingly. Now, when we talk about matrix nanocomposite, metal matrix, or any type of matrix with embedded particle, there are different types. Matrix reinforced with particles, you can clearly see matrix is there. Your matrix can be metal, your matrix can be ceramic, your matrix can be polymer. You are aware of it. Depending upon the type of application, you can fix it what you want. Also, you have to see the processing conditions are present in order to make those material. So matrix reinforced with nanoparticle, you have matrix reinforced with nanowires and nanotubes. Cartoon looks like this. Then you have laminated structures where you have nanowires or nanotubes that are laminated on sheets. And then you have sandwich structure like this. You have particulate, and then you have laminated at both the end. So this is called layered nanocomposite, and this is called matrix reinforced nanocomposites. And these both type of materials are, if they are designed properly, you can control the chemistry. Motivation behind the control of chemistry can be density, and you have to understand whether the material that you are making is stable or not, and based on that you can design them. Now here are another way to show you. Particulate are basically called 0D, wire rods and tubes are basically called 1D, and layer structure you are basically getting from two-dimension structure. So you have 0D structure in some type of, say, let us talk about bulk nanocomposite here. So 0D in bulk material, you have 1D in bulk material, you have laminated structure like this thin film on substrate, or you can also have bulk nanocomposite resulting from this particular surface. You can cut in multiple pieces, you can put it inside them. All are the class of nanocomposite material. Otherwise, these are typical examples of nanocomposite put over certain substrate. Thin film is there, nanocomposite in a form of 1D structure and nanocomposite in a form of a 0D structure. So this is okay. And apart from that, there are different type of structures that are possible. You have I want to show you different type of structures so that you understand what are the varieties of materials that can be made. So you have substrate onto which you put a film. This is a single crystal film. You can have some boundaries are observed. We call it a crystalline film. These boundaries are bigger in comparison to this. We call it a microcrystalline. This is nanocrystalline. So similarly, thickness is a very important criteria of the film because you are making structure. Structure requires some type of surface property. Surface resistance should be there. Material must be hard on the surface. Definitely, you require to do some certain type of surface modification. And this is an example of certain type of surface modification people are doing on suitable substrate. And this can be engineered and understood well if you have a good idea about the substrate and the material that you want to deposit. Not only that, sometimes you want to engineer your material to give different type of features. Sorry? Sorry? So there are different type of features, like you have square features, V features, U type of features that can also be given in such structures. Depending on what you want to do with these structures. Normally, this type of structures are dealt in electronics material or electronic system in order to create some type of layer or some type of material inside this particular layer. Now, I'm going to talk about some processes by which you can make the materials which I have talked about, because I talked about film. You keep on growing film, it may so happen film will grow over one another, you may end up in getting the bulk film. So, there is something called deposition. You can have the substrate material, whatever gas species will be coming, you will dislodge the material that you want to deposit, and then you can deposit here. So in this way, the deposition is going to take place. There are different ways by which deposition can be done. Okay, there is a chemical vapor deposition, physical vapor deposition, atomic layer deposition, molecular beam epitaxy. There are different type of deposition are there. So there is different classes of depositions are there, and whatever is our end need, we can understand. So whatever we need, whatever type of structure we need, we can understand with the help of whatever deposition we want to do. Apart from that, with the help of micro machining or nano machining, you can also develop certain nanostructure features in your material. I'm just giving you an idea that the variety of nanostructured features that are available, in order to synthesize them for specific high-end application, what are the challenges for making those materials, and what are the feature definition of those materials when you want to work with them. So as I told you, depositions can be physically, you want to deposit material onto the substrate. Chemically, you want to deposit material substrate. So it basically looks like this, that you have a chemical vapor deposition. You want to deposit any species onto the substrate. It comes via precursor cylinder and it get deposited. So this is the way the thin films are made. Sputtering is an example of PVD, where you want to deposit species one by one over the substrate material. So what we are doing, we are talking about 2D materials where structural modification can be done over the surface. If all this process normally have certain impurities associated with precursor, certain impurities associated with environment. You can take care of, as I mentioned you, that if you want to make a material where the material property must meet your expectations, design expectations, you must be able to make those materials using very sophisticated technique. So these techniques may not be too sophisticated, because you do have the environment do have impurities, they may come into your material. So we have to rely on atomic layer deposition, where you deposit atoms by atoms. You have a good control over atoms so that no impurity can participate in deposition. So in this way, you can make a very good quality film that can be used for the application. So, and also you can have a good understanding about the properties that you are getting out of the atomic layer deposition technique. Now coming to the bulk nanostructured materials. So you can have something called, ball milling. You can have a big ball milling setup, where tons of powders can be synthesized. You have a vial, you have a powder precursors. Say for example, you want to make aluminum and copper. So you can have aluminum and copper, and then you can have balls that will be rotating in the drum in anti-clockwise direction. And then the impact is so high, the kinetic energy between the ball is so high that always there is a reduction in the powder dimension is going to take place. And then you have taken the standalone element. This element is going to combine together in order to form some type of combination of two elements, what we call as an alloy. So this is the way by which bulk nanostructured materials can be made. Not only this is in the form of a powder. So this particular paragraph indicates that between the powder. So this is the ball, this is the ball, this is the powder, and between the ball, powders are coming and they are getting welded. So they get trapped first, they get deformed, they get welded. There is a limit to sustain stress on such particle. Once that stress level is crossed, the particle is going to break. That is what the breaking phenomena, multiple time it happens, you end up in getting what is called nanostructured material. So this is the way you make the powdered nanostructured materials. Now you can take this powder, you put it in some type of sintering machine. It can be hot isostatic sintering machine, big sintering machine, or it can be some type of plasma sintering machine where you want to avoid impurity from environment, and you can convert them into bulk nanocomposite material. So that is a particulate technology route or powder technology route in order to make the component out of the powder. So now by this time you have a clear idea that the nanomaterials have high surface area to volume ratio. They have high surface area, they have high surface energy, they do have a good motivation to interact with environment. If it interacts with environment, it may break up. If the breakup is not good for the component will fail. If breakup is able to manage itself, self-healing capability is there in material, then those breakups may self-heal also at the same time, then it will lead to smart material. And then we have also observed contact angle and how it is related to interatomic distance. Then we have seen there are some few examples of synthesis process to make two-dimensional and three-dimension material. There are many more. There are many more examples. I just shared few with you. Now you want to take this material. You have made this material. You want to take this material for some pilot plant production. But before pilot plant production, you require to do some type of testing. That a laboratory testing is involved. So now we are going to talk about certain features you want to see from the material. Now let us talk about mechanical property. So for a polycrystalline material, the crystals are very big. And when the crystals are very big, which means the boundaries there, the boundaries are small. Okay, but what happens in nanomaterial? The boundary region becomes larger and the crystals becomes smaller. And when the boundary becomes smaller, and boundary is known to be disordered region, so what we say is that the percentage of disorderness is increasing as you go from polycrystalline material to nanocrystalline material. This is what is all about material, from polycrystalline to nanocrystalline material. Now, with this disorderness, you imagine if you are making anything disordered, that disordered material will tend to come to ordered state. How it will come? By reacting with environment. It will come to the ordered state. Now, if you are able to manage the disordered state, because disordered state has a lot of energy. If you're able to manage the energy of the disordered state, it may so happen that you may end up in changing its internal structure, and that is how people are engineering the structure of materials with the help of disordered structure that is being coming out from the nanostructured material. So this is to give you idea. This is a very big periodic arrangement of atoms. Periodic arrangement of atoms. You see, I have a boundary, Y type of boundary. But you see now you have created disorderness. They are random, completely random. There is no boundary. So which means this proportion you see here has been converted into this. So you have created a lot of instability in material when you come from this, crystalline material to total disordered material. And this disordered material is an avenue for you. Either you leave it as it is going to get destroyed by reacting with environment, or you try to engineer it and convert it into suitable material for your choice. Now, you must understand one thing, that when we talk about bulk material are having continuum property. So you take 1 kg of bulk material, you take 1 gram of that material, you both will be having similar property, same density, same melting point, same strength, same hardness. But when you talk about nanostructured material, say you have taken copper, for example, bulk material. Now you have converted your copper into nanostructured copper. You will not be having the same continuum property. Your bulk copper is a good conductor of electricity, good conductor of thermal energy. But your nano copper is an having insulating property. Why? Because your bulk copper has now is in nanoscale. So it has confined the mobility of electron by which you were attaining the electrical property and thermal property. You have confined it. So your electron is not able to get mobilized. It is not having enough energy to cause the energy barrier. And that is why when you go from same material, change in structure from microstructure or macrostructure to nanostructure, you change the property. So what I mean to say that your continuum mechanics does not work in nanostructured material. So you will always see difference in property. Whatever property you have registered till time in any of the standard handbook, in order to understand its property, is not applicable to the nanostructured material. So nanostructured materials altogether is a different class of material. So when we were talking about continuum mechanics, job was very easy. But now when we talk about nanostructured material, as I mentioned you, there is a huge gap between both of them, and your continuum approximation does not work. And when your continuum approximation does not work, then you will observe some change in property as you go from big material to smaller material or smaller structure material. And what people have observed that these smaller materials are stronger. Now you see, some time back I mentioned you take a monolithic copper or monolithic gold, you will see that its melting point is reducing. I have told you that its strength is reducing. That is good for monolithic material. It's a standalone single material. But when you talk about materials like this, steels, magnesium, aluminum alloys, magnesium alloys, titanium alloys, where you have mixture of material, you generate nanoprecipitates inside them, and these nanoprecipitates does not allow your material to deform. And when it does not allow your material to deform, your material becomes stronger. And that is how people have achieved nanoscale dispersion of these particles, and with the help of that they have got the properties that was not seen in micron size material. Now this is a typical example, accidentally made alloy, that is aluminum 4% copper alloy. You take this alloy, you make this alloy, what you'll observe that both of them have different atomic radius. If you heat, there is expansion of material, due to which there is a good mixing between aluminum and copper. But if you bring it back to the room temperature, still you will see no change. It looks like a single phase material. But now if you heat this alloy at 550 degrees Celsius and rapidly cool, your copper remain dissolved. But copper atoms slightly distort the aluminum crystals. They start precipitating out. If you give little energy for copper to precipitate out, they will take the shape of this. It is called COL2 phase. So they take the shape of some needle-like particle. You can see with the help of this micron marker that what is this needle-like particle. Now what you have done, you have taken the macro size material, you have given a suitable heat treatment to it, and then you have ended up in getting what is called needle-like particle, and they have nano dimension. And this was accidentally prepared, but with the advent of electron microscopy, people could understand why such type of system are having high strength. Otherwise, you imagine if you don't have electron microscopy, you won't be able to understand what is happening in such type of material. So the coming of characterization technique in order to understand structure and understanding that your structure can be changed from micron to nano with the help of suitable energy. When they have brought both of them together, people have generated that there is a good chance for structure property manipulation to make the materials of desired property in nanostructured material. So that is how the motivation as far as the material is concerned. people have. Now, you see, I was mentioning you about this particular system. You take the hardness, which is a indication of strength. You aging, you keep on, you take this material, you keep on aging because you have aged at 150 degrees Celsius. But how much time you have to age? So you can keep on aging for 0.1 hours, 1 hour, 10 hours, 100 hours. So people have observed a maturity in precipitate is achieved at 100 hours. Your precipitates are now fully stable and grown 2 nanometer wide, 30 nanometer long, 30 nanometer apart. And that allows you to conclude here that you have a nanoprecipitates coming out of aluminum 4% copper alloy that gives strengthening. So this scale also indicates that the type of strength you have achieved as far as weaker hardness is concerned. So most of the high strength material we use today have been produced over the period of time, derive their strength by nanoprecipitation. So what I mean to say, because of the advent of newer characterization technique, we are able to see the dynamics of nano phases inside the material. Otherwise, earlier it was like people were not able to understand. Now we could understand how the structure property relationships are getting developed. Now there are three ways by which this is happening. Either your atoms are dissolved, but they do have some physical features present inside the material. So when you deform the material, this dissolved atom resists the deformation force. Your dislocation line is observed here. So you call it a solution strengthening. When you have a discrete obstacle, which are of nanoscale dimension, okay, you will see that they will also obstruct the deformation force, what you call as a dispersion hardening. You can also do mechanical work on the material in order to create the dislocation jungles. And when you want to deform this material, dislocation is going to stop dislocation. So see, here the small particle, this is the precipitate, bigger dimension, and this is a dislocation jungle. All have different names: solution hardening, dispersion hardening, and work hardening. So this is the way you can impart strength in your material. But see the three strategies here, all the three strategies rely on nano type of features. Your dislocation is also of nano, your precipitate is in nano dimension, your atoms, dissolved atoms are also in nano dimension. So it will be interesting to develop an idea to gain further understanding that how we can manipulate the property of material with the help of all the three type of mechanisms we have discussed just now. Okay, so we can engineer the structure, we can engineer the precipitate, we can engineer the type of atoms, we can engineer the mechanical deformation practices such that we can enjoy the property given by solution strengthening, dispersion strengthening, and work hardening. Now, the question arises, yeah, I have told you roughly some time back that your strength is improving because of presence of this precipitate. And I also told you that they obstruct the mobility of your deformation force in terms of dislocation. So dislocation do have certain features which we require to understand. This is also applicable in any type of nanomaterials which you want to use in a form of a nanocomposite, or maybe it may be a nanomaterials where you have nano features present in it. You can apply these rules in them and then try to understand why there is a strengthening taking place. And at the same time, keep in mind that whatever phases are present, you have to understand the interrelationship between these two phases because they are creating an interface. So what type of interface it is creating? So now the question arises, why should finely divided or structural materials have properties that differ from the conventional materials? I have already mentioned you some time back why it is happening, but still we have to keep probing because that gives you opportunity to change the property. And why does almost anything with nanoscale structure have unusual property? You have some clue now that why there is a change in property, and a very good clue to you is your surface area, surface energy, surface bonding, interfacial bonding, interaction of smaller feature with a smaller feature. Your smaller feature is deformation force in the form of a small dimension, which is interacting with the features which are also present in smaller dimension. And that is how you are able to see the nature of material. Now let us see one interesting thing. This is universal observation. I am going to share with you some couple of observation. Hardness versus grain size of copper. You know, everybody has done such type of experiment before. You take your hardness from bigger scale to smaller scale. What do you observe? Your hardness will keeps on increasing as you keep on decreasing the grain size. Interesting. But this also indicates that it keeps on going up. No, no, no. It should not keep on going up. There should be some level where it should get stopped. Such type of scale does not give you much idea, because it says that it will even cross this limit, which means it will cross the ideal strength. And we do have habit to extrapolate these type of results. We can keep on drawing the straight line, and then we'll say that if I'm going to 0.1 nanometer, I'm going to get the 5 GPa hardness. And then you will convert it into strength. You will say that this much strength can be observed. But practically it is not possible. Why? Because the graph which you have drawn is wrong. So you have to draw graph in logarithmic scale. If you draw such graph in logarithmic scale, you will see that your hardness though keeps on increasing, but it starts flattening the curve. And that starts flattening the curve is called the breakdown of hardness. And a very well-known rule is their Hall-Patch relationship, where you say that the yield strength is going to increase with decrease in grain size, but there is a limit up to which the grain size can if you know can influence your strength. After some time, after some dimension, it will not be able to influence your strength. So breakdown of Hall-Patch equation is going to take place, and after this no more strength you will observe. So this is something which is important. So what I mean to say, the take home message here is, we want to make material for application. We want to make composites material. We want to make monolithic material for designing our material, aerospace application. But we should also know that what is the level of analysis we are doing, what type of analysis we are doing in order to fit the design aspect. And sometimes it so happens that such type of analysis are very important in order to understand the property of material. Now, why there is increase in strength with reduction in grain size, this could be understood. Okay, why there is increase? Because the dislocations which are of nanometer dimension, which is being initiated by the pressure or type of stress that you have given to material, they are getting obstructed by the small features in a form of atoms, in a form of a precipitates, in a form of a dislocation jungles. So that was the reason which we have discussed some time back. The dislocations are not easily passing through, and you require a lot of force for your dislocation to move from one end to another end, and that makes your material to gain strength with reduction in dimension. Now, there is also something you must know, that now such type of studies like have been done for different type of structures. Like for example, you take the grains, your material, material will be having some features at the smaller scale. That small scale structure people normally deal in form of such type of figure. So this is a dislocation pileup that has taken place inside the grain. Okay, when you're applying stress. So when pileup is taking place, strength is taking place. Now, if it is able to jump from one grain to another grain without any obstacle, of course, your material is going to move. It's going to flow, and you will lose the strength of material. Same thing is going to happen with nanolaminates or nanolayers. You provide the stress, you have the dislocation pileup taking place. So here is an example. It talks about that you have an interface in a form of a grain boundary where dislocation comes. It does not have enough strength to pass through. If it is having a lot of dislocations coming here, if it can pass through, it will jump to this slip line and then slip lane, and then it will go to the different grains, and in this way you can deform your material. So this is well established technique. So now the question is, why they are becoming saturated here? Interesting thing, why they become saturated. So up to here we have understood that we are able to obstruct the mobility of dislocation. But after some time, you keep on making this smaller and smaller. You make this layer smaller and smaller. What is going to happen? Your dislocation won't be able to find a suitable position inside that particular grain, they won't be able to adhere inside that particular grain. So when they are not able to adhere, automatically they will go away from that particular grain because they are not stable in that particular geometric dimension. And in this way, when you make your material smaller and smaller, you are not able to stop dislocation because you have no more strength in order to stop dislocation because your grains have become small. The dimensional stability has to come. Your now grain has come to the dimension of dislocation, and dislocation is now able to bypass that particular grain. And that is why we observe this type of feature in materials. Similar case with nickel with normal scale, and you do with logarithmic scale, same thing is observed with nickel. So there is something breakdown is taking place in the material. So this is a very important that I want to make nanocomposite material for aerospace application. It's okay, but we have to understand certain challenges. These challenges are these challenges, what I'm talking about. One is your melting point, the challenge which I have mentioned. Another is that all not nanomaterials can give you. There is also something that is happening. You have to understand a good balance between the dimension and its stability with the force or deformation that you are giving to the material. The nanolaminates are widely used in various aerospace application in order to strengthen the composite material. This is observed this is manufactured by sequential evaporation of different layers. Okay, but again, I'll take a simple example of copper nickel layer. Okay, say copper nickel multi-layer structures. You see here, I have talked to you some time back that with the decrease in dimension, you are going to increase the strength. Now this is the tensile strength. Okay, now if you reduce this dimension, what is going to happen? You are also going to get the breakdown. So what I mean to say, irrespective of the type of material, irrespective of the type of internal structure, there is always going to be a limit at which your material is not going to respond to strength, and what you are going to call that particular phenomena as a breakdown. And we must have a good understanding at what particular boundary of your material is going to become weaker. We must have a very good understanding, and that is the reason I say that, if you remember, I have used that we require to test material. A lot of work has to be carried out in different materials in order to give a proof that yes, these materials can withstand the type of property we want from the nanostructured composite or nanostructured monolithic material. So I'm coming to the conclusion here. What we have observed is, yes, you take the different, this is the ASBE chart. You take your nanowire, you take your nanomaterials, nanocrystalline materials, you take ceramic nanocomposites, you take metal nanocomposites, you take polymer nanocomposites. You see, these all are very good news for us. These are all very good news for us. That there is improvement in strength. Okay, and also there is a density management can be done if properly understood what type of composite is to be used. So polymer matrix composite or metallic matrix composite, or you have some gold is having high density. That is the reason this type of materials are coming in somewhere into the 10 gram per cc type of scale. But yes, the good news is that they are having suitable position in the ASBE chart as far as yield strength is concerned. Now, important thing that we have to keep in mind that yield strength, tensile strength, these are all the property that are the function of internal structure of material. Internal structure means, I mean to say, microstructure of material. So you keep on making your microstructure smaller and smaller, you go on nanostructure, and when you go on nanostructure, that is what you observe. That is what you observe. Okay, now similar is the case with tensile strength and density. Everywhere nanocrystalline material, nanocomposite material, 3D nano ceramic composite material, polymer CNT, carbon nanotube composite materials, they do have good tensile property in comparison to monolithic metal, ceramics or alloys, or any type of foams or polyester or elastomers. So there is a light at the end of tunnel that nanostructured materials can be used. But I gave you two challenges. The two challenges are, one is their melting point. Good understanding of melting point with reference to matrix material should be there if we are talking in terms of composite. And second, you must also understand what is the desired dimension of the phases or desired dimension of the grains which you are making with the help of suitable process, because there are n number of processes in market which can make nano structured material. You should have a good understanding followed by good study of mechanical properties and correlating it with structure. So there's huge good number of job is to be done, and our my whole presentation was to give you idea that not all nanostructured materials are good until unless it is understood properly for respected application. So with this, I will thank you all to be patiently hearing to me.
Sir, thank you very much, sir. So participants are posing the questions.
Yeah, yeah.
So how Akshat Patel is asking how to make the surface of CFRP plate conductive. What kind of filler can be added into the matrix?
Sorry, carbon. What is that? Carbon reinforced fiber
CFR,
composite, right?
yeah.
Carbon fiber reinforced composite. And what he's asking
What kind of filler can be added into the matrix?
in the matrix in order to make it conductive.
Yes.
Great, good question. See, you're already talking about polymeric material here, carbon fiber reinforced composite, and you're talking what type of filler materials can be introduced, because I understand that we do require some functional properties to be incorporated in materials. Probably for testing, that is the inline testing, or sometimes we want some type of sensing properties. Now, polymer goes well with polymer, and there are conductive polymers available. So you can use conductive polymers. They have less density. They can be stabilized with the help of polymeric stabilization technique, and that can be introduced during the process.
Yes, Karthik, you can ask. Sir, can you be a bit louder? Karthik?
Sir, can you hear me, sir?
Yes.
Sir, we are developing a thin film, sir. In the thin film called as a 2D, two-dimensional nanostructure. In that region, we lot of nano flower-like structures are developed. Flower-like structures are growing, sir. How do we call it? That's a two-dimensional or three-dimensional
Karthik,
nanostructure,
your
sir?
voice is breaking.
Karthik, can you please post it in the chat box?
Yeah, please.
Any other questions? You may please raise your hand. Akshat, is it the same question you asked before also? Okay, how to make the surface, same question.
Sharath, I'm taking one lecture right now.
Karthik, are you posing your question here? I think it will take a little while for him to
Yeah,
post
yeah,
it.
yeah. What I understood is that Karthik is making some material, and he mentioned that some type of one-dimension structure is coming in a form of a flower. And then I don't know what he wants to ask in that. It seems to be interesting question to me as well. So I'll wait for his question.
Sure, sir. Meanwhile, I request all the participants to please fill the feedback form given in the chat window. Okay, you want the WhatsApp group link. The WhatsApp group link also has been shared in the chat window. Feedback form is not active. Sir, I have already received 6 responses on the feedback form, sir. Sriram Prasad Garu.
But after the email, is not taking the name and all. Is there any problem? That's why I put that. Only name, email is taking. After that information, it's is not taking. That's why. Please check. I'll try again.
Nirmit sir? Nirmit sir, are you there?
Yes, yes. Only email typing is taken. Afterwards, name and all typing is not taking.
The people are sending, sir.
Okay, I will try again. Then I will.
Can any of the co-hosts please check with the feedback link? Is there any problem? So Karthik is type.
Yeah.
Yeah, we are developing a thin film. In the film, lot of nano rods are growing.
Okay.
Now my question is, thin film is 2-dimensional structure.
Okay.
Rods are called 3-dimensional structure.
Okay.
So how?
Yeah.
He's asking.
Very good. So I really don't know that what type of film is growing, and also don't know the type of flower it is forming, but one can tell that what is happening. Okay. So if I'm not wrong, he is not growing any single material film. So if the rod is forming, which means nucleation is happening. What is the meaning of nucleation? That some type of droplets of some type of other material is getting segregated at certain location, and that particular droplet is squeezing the material from the thin film, due to which the growth is happening in particular direction. Now why this happens? That particular droplet which is formed, say for example Karthik is making thin film made up of AB, and it so happens that if he's not controlling the temperature or not controlling the environment, it is possible that in place of AB, AB2 may form. Just a hypothetical example. This AB2 which is forming will be a liquid on the AB. Now this AB2 has a tendency to grow in single dimension. So what it is going to do? It is going to take AB and it is going to house in AB2, and it will grow in one dimension. So this is what happens, and this is a function of crystal structure. So if Karthik can tell me in detail what type of material is going by what method is growing, then I can tell that what exactly is happening in the overall scenario and why he is getting one dimension structure in two-dimensional film. It is normal practice. You may get it.
Karthik, can you please elaborate your question? We are applying for tribological applications.
Yeah, but
It
what
is
is
a
the yeah.
It's a nano composite.
But yeah, what is that substrate material, and what is the, I mean, any idea on substrate material he wants to give us?
Substrate materials, Karthik. Can you please type it?
Or these are all patented thing. Probably Karthik may not want to share with us. I don't know really. So if Karthik can also drop me an email, I will definitely respond.
Okay. Sir, can I share your email with
Yeah,
the
yeah, sure,
participant?
sure, sure.
Okay, sir. Sir, Jatin sir,
Yes,
JATIN.BHATT.
at mme.vnit.ac.in.
Okay. It's mme.nit.ac.in.
Yeah.
So, Karthik, you can directly mail to sir. Any more questions? I have seen 2 or 3 people raising their hands. So, so thank you very much, sir.
Yeah.
Uh,
Thank you.
Actually, HOD sir has gone for an urgent meeting.
Okay.
So, on behalf of him and the entire aeronautical department of MLR Institute of Technology, I kindly thank you for taking out your time and also answering the queries patiently.
Thank you very much.
Thank you
Thank you.
very
Thank you.
much, sir.
Thank you,
We
Shweta.
look forward for future uh, collaborations too.
Sure.
Thank you,
Thank you.
sir.
Thank you, Shweta. Thank you. So I'll go out now. Okay.
Yes, sir.
Okay.